Hello, everyone. My name is Jiamin Hu. I am one of the organizers of this online workshop. I am currently a postdoc at the University of Florida and Max Planck Institute for Extraterrestrial Physics. In this talk, I am going to discuss our parity analysis for the Bot sample with a focus on systematics and also the covariance. But if you have general interest in systematics for galaxy surveys, in this workshop, we also have a nice pedagogical talk by Ashley Ross. And in addition, we have also a roundtable discussion about the endpoint statistics and parity violation, and you are welcome to join. Since this is the second week of a parity workshop, I will only give a brief introduction to the parity and galaxy's 4-point function. So the parity transformation flipped the spatial coordinate from the XYZ to minus XYZ. And here we indicate the vertices of the tetrahedra as galaxies. And from each vertex, if we arrange the R1 to be smaller than 2 than 3, then we can assign an effective handedness to each vertex. And after applying a parity transformation, we can see that the handedness is flipped. If we imagine we repeat this process for a line or a triangle, we can always recover the original image by rotation. However, if we apply this to a tetrahedron, the transformed tet will not be overlapping with the original one. And this means two things. So first, in 2D, the parity transformation equals rotation, while in 3D, the parity transformation is a mirroring operation plus a rotation. And second, if we consider scalar fields, we need to have at least 4 points to be sensitive to the parity transformation. So we performed this 4-point function analysis on the 2 subsamples of the BOSS data. And the left hand shows the footprint of the CMASS sample. To the upper panel, it shows the northern galactic cap, and the lower panel shows the southern galactic cap. And on the right, it is the number density as a function of the redshift. So the CMASS sample is at a higher redshift range that goes from 0.4 to 0.7 with about 800,000 objects, while the low-Z sample sits at a low redshift range from 0.2 to 0.4 with about 280,000 objects. So the analysis methodology is as follows. We take the BOSS sample and we measure the 4-point functions. And in particular, we perform a radial and angular separation and then express the 4-point functions in the isotropic basis functions. The choice of this basis function is motivated by the rotational invariance of the system. There are much to talk about regarding this basis function, and you can find more detailed or discussions in the paper by Khan and Slepian. And in the next, we compute the chi-square. So here we performed a model-independent search with a null hypothesis, which means that we set these two theory terms to be zeros. And finally, we compute the chi-squared value of the measured data to the empirical distribution from the mock simulations. And the separation between the orange vertical line and also this black curve indicates the detection significance. And last year, there were 2 papers performed the analysis on the BOSS sample. And I would say both papers actually followed very similar methodologies with some differences in the choice for the radial binning and the choice of the sample, and effectively it becomes a question of the galaxy weights. Now that our goal is very clear, we want to compute the chi-square, but where is the challenge? If we come back to the definition of the chi-square, there are 2 components that enters this number. So the 4-point function or the signal and the covariance that quantifies the arrow bar. And this is basically saying we need to worry about the contamination at signal level and also at the covariance level. So first, at the signal level, there could be instrumental systematics, observer-related effects, and algorithm-related effects. And then coming to the covariance level, there is a question of how we estimate the covariance. And here the instrumental systematics enter again. And another question is the fiducial cosmology. So before I proceed, I would also like to make a few statements, and these are my personal opinions towards these challenges. So first, I want to say that the contaminations at signal level are less worrisome, and that is because intuitively, in order to realize a parity-violating structure with scalar fields, we need to form a triple product of vectors, and these triple products need to live in a 3D space. Therefore, if you want to contaminate at the signal level, those effects also need to be 3D, and there are not many of them. But in contrast, there are many uncertainties in estimating the error bars. And I want to point out that this is a very different analysis than those when you have a model and want to use the model to fit the data. And in those cases, the accuracies in the covariance propagates indirectly into the parameter constraint through the likelihood marginalization. However, in our case, when we apply the null hypothesis, the error bar is directly associated with the detection significance. And here I might say that all survey-specific effects are potentially important. And later I will come back to explain what do I mean here by survey-specific. And another point I would like to make is that the concerns regarding analytic covariance matrices should be rephrased as how well do we understand instrumental systematics and fiducial cosmology. And I will also come back to this point later. So let me start with the signal level contamination. And here I just want to give one example of one instrumental systematic that we worried about. This particular one is the redshift failure. So since BOSS is a spectroscopic survey and we measure the galaxy's redshifts, but we don't always succeed in obtaining the redshifts due to various reasons like broken fibers, CCD cameras, seeing conditions, and so on. So as its name suggested, the fraction of failure in obtaining the redshifts is the redshift failure. And as we said before, we are interested in 3D effects. So how does that work and how do we put everything together? So here on the left, I show a photo of the BOSS plate, which I took during the WAS meeting. In this photo, we see not only the BOSS aluminum plate, but also the fibers that were plugged into the host of the plate, and also the tasty SDSS M&S chocolate. And here on the right, it shows the focal plane indicated by the circles. And then here, these moving yellow dots indicate the fiber bundles that were plugged into the plates during the entire observing epochs. So after averaging the positions of the fibers, we found that they were not just randomly plugged into the plates, but rather they have their preferred locations of each fiber, as indicated in this lab panel. So in the middle panel, we plot the fiber redshift efficiency as a function of the fiber IDs. And we can see a clear M-shaped patterns here. And this pattern is highly related to the edge of the spectral graph. And as we approach the edge, the efficiency drops. So here on the right panel, we can see that there is a slight asymmetry in the efficiency on the 2D focal plane. And now that the galaxies with higher redshifts are fainter and they're more likely to suffer from the redshift failure effect. And that is one example of how a 2D systematics can be promoted into a 3D one. So in total, there were about 1.8% of the objects suffered from the redshift failure. And since we already lost this redshift during the observation, and there is no way to retrieve those redshifts, however, for our analysis, we can make it worse to see this impact. And therefore, we doubled the effect by throwing away another 2% of objects. But the takeaway is that we found this procedure shifted the detection significance upwards by 2.5 sigma. And the good news is that the effect is not enough to explain the detection significance. And this is a busy slide, but here I will just try to briefly summarize more effects that we thought about and also worried about during the BOSS analysis, including more survey-specific effects, such as how we handle a fiber collision where we lose redshifts because neighboring galaxies cannot be resolved by one fiber during a single exposure. And regarding the observer-related effects, such as the Kaiser rocket effect and the tidal alignment, where both effects can lead to modulations in the density field along the line of sight direction, and they appear as a quadrupole and the parity-even. Regarding the algorithm-related effects, the survey has irregular footprint, and there we need to correct for the survey geometry, which leads to a mode mixing, but we also found this effect to be very small. And we also try to split the skies into different patches and search for anomalies, and we didn't really find any outliers. So what we learned here is that, again, come back to the previous point, it is kind of hard to come up with systematics that contaminate at the signal level. But now let's come to the covariance estimation. So since the data vector of the 4-point function has a large dimensionality, we saw before that in order to compute the chi-square, we need to invert the covariance matrix, and the matrix itself has to be positive and semi-definite. And effectively speaking, we need more marks than the size of the data vector. And given that we had only about 2,000 marks, they were not enough to invert the matrix if we use all of them. And therefore, the analytic covariance was a centerpiece of this analysis. And apart from a broad good agreement between the mark and the analytic covariance matrix, and we can see from the right panel, where this lower triangle is the mark covariance and the upper triangle is the analytic covariance. There are caveats of the analytic covariance as listed below. And they include like the Gaussian approximation, survey geometry, and higher order power spectrum multiple correction to the covariance structure. But just a quick note that this last point is not equivalent to the redshift space distortion, but in fact, the covariance knows about the leading order RSD, and we have tested this also in our previous paper. And now comes to an interesting question that whether the difference in the two BOSS paper is caused by the covariance. And the short answer is not really. And in fact, we used almost the same analytic covariance matrices up to some calibration parameters. And we'll also have more dedicated discussions during the roundtable session. So now if we put aside the analytic covariance for a while, an additional test we did was to calculate the detection significance by purely mark-based covariance. And here we applied the cuts in the data vector to force a minimum radial band separation and a cut at the large scales, such that we can reduce more nonlinear modes and also reduce the concerns about the large-scale systematics. So here in the left plot, we still see that there is about 5.5 sigma detection, and the empirical chi-square distribution matches very well with the expected one. So this test does not involve any analytic covariance matrix, and this was also about my previous statement about the concerns regarding the analytic covariance matrix and also the systematics. So if we could have fully trusted the mark covariance, we could have probably celebrated a bit more. However, we still need to worry that the systematics implemented in these marks do not fully capture the survey realism, and it might underestimate the error bar. And also these marks themselves are also based on approximated method in gravitational evolution. And they also rely on calibration and also parameter tuning. And then there is also a question about our choice of fiducial cosmology. So we did some tests by changing the omega matter by around 3 sigma of the Planck error bar, and saw that this was also not enough to explain the detection significance. But overall, there are questions, or these are questions that are not so straightforward to answer. But one thing we could do is to use the parity-even sector as a self-calibration. And since the systematics induced fluctuations reflects essentially at the density level, so it is not so bad to assume that if there are such systematics and they are likely to induce variance equally for parity-even and also for the odd sector. So based on this logic, we performed a test where we used the result from the parity-even sector to rescale the parity-odd one. And after doing that, we still found there is non-zero detection. So this is kind of reassuring, but there are certainly more work to be done in the future. And so now what is next? And looking to the future, one thing we are quite excited about is the data from the dark energy spectroscopic instrument, the DESI at Mayo's telescope. It is a successor of BOSS, and these two surveys, they share a lot of similar designs. So far, DESI has been doing a great job and has collected about 20 million galaxy spectra. And it will also use a fiber system, but it will have improved imaging and different tiling or observing strategy. And here we also made a forecast for the DESI parity violation surge. So although this forecast is very ideal, but the takeaway is that we should see a higher detection significance than BOSS if there were a real physics-induced signal. And in addition to DESI, there are also more galaxy surveys such as Euclid and also Roman. So this is going to be very excited, and let's stay tuned. And thank you for your time, and thank you for listening.